Welcome back to the last part of this talk, which I promise will be rather brief. I put again a combination of the pictures we've seen before. So here you see the sketch of the metrics gamma k that converge to the metric gamma infinity in our theorem, consisting each gamma k consists of a region where we talk about the color, and the region in blue, and the region which is called a bridge in green, and a region in orange, which is a Schwarzschild of mass nk. And I've told you more precisely that it's actually a cutoff and maintained version of Schwarzschild, which is indicated in red here. And these metrics on the manifold 0 to infinity with 0 included cross S2 converge in C1 alpha and compact subsets to the metric gamma infinity sketched at the bottom, where we have a cylinder, meaning not that its cross sections are round, but all the cross sections have the same constant area, and this is glued to a Schwarzschild all the way down to the horizon, with mass consistent with the Penrose inequality, bound and equal to that from the left-hand side in the limit. So that's, in a nutshell, what I claimed so far that we proved. In fact, we didn't just find one sequence for each G0, but we found a one parameter family parameterized by this parameter epsilon that already appeared a little bit in the proof sketch of the theorem by Mantelidis and Shane that I showed you. And so there's an epsilon 0 depending only on this G0 so that for every smaller epsilon between 0 and this epsilon 0, gamma epsilon converges to the family gamma epsilon exists and converges to this gamma infinity. And actually, we think that we can extend probably this convergence from C1 alpha on compact subsets of the manifold to a weighted version of the CK space, probably C1 alpha, and maybe also Sobolev spaces with weights at infinity to account for the asymptotically flat end. But this is work in progress, so I wanted to write it down. So what quantitative changes do we need to make to the Mantelidis chain construction in order to get this control that allows us to prove this convergence? And let me say again that it wasn't clear from the construction, and it was a question that was frequently asked in talks, whether this color region would explode to an infinite cylinder, stay of finite length, or collapse. Same for the bridge, and whether this bend-in and cutoff on Schwarzschild, what behavior this would entail in a potential limit. And so the sequences or one parameter families we find have a finite length cylinder limit of the color and a finite length cylinder limit of the bridge, and the bending in and cutting off of the Schwarzschild disappears in the limit. But that doesn't say that you cannot pick the parameters involved and all the quantitative things I'm going to talk about in a minute differently and actually obtain something else. We haven't tried. It's conceivable, but we can pick parameters and other details so that we get this family with this limit for the given G0. Okay, so here again is the color specification of the Mantelidis chain paper, where A is a positive parameter used to stretch up the color so the scalar curvature becomes positive. Use the first eigenfunction of the operator involved here. F epsilon is this radial profile that opens up what would otherwise just be a constant radial cylinder, and of course goes away as epsilon goes to 0. And T is a parameter between 0 and 1, and theta was a threshold less than 1, after which this family of metrics G of T, this flow of metrics, was round, so constant in T time. Okay, so this is the type, and what we need to control in order to get our estimates in this color region is we need to pick A carefully, depending on 0, not on epsilon. Epsilon is the parameter, so in the sequence it would be not on K. And this relies on ideas in the paper by Miao and Xie from 16. Where they introduce a parameter alpha, and we use this parameter alpha to construct the A that we need explicitly in terms of this parameter alpha, which in turn is a parameter depending on the G0. Okay. Then that's for the color. That's all we need to do. The A can be picked independently of epsilon. This eigenfunction mu doesn't depend on epsilon to begin with. And this f epsilon depends on epsilon in a very obvious way. And the flow of metrics g of t doesn't depend on epsilon either. So the only place where all of this depends on epsilon in the color region is in this radial profile of epsilon, where we have precise control, and you would probably believe me if I tell you that this f epsilon goes to 1 nicely enough for this whole thing to go to a cylinder across the constant area of the cross sections, independent of t. Recall that this family D of t had constant area independent of t. Okay, so then the next region, let me go back to the picture. So we've dealt with this blue color region on the left now, and we've chosen this one parameter A there to get more quantitative control, which is enough to get all the estimates we need in the color region. And some of the estimates going into the bridge region, actually, as a matter of fact. And then in this Schwarzschild region, of course, we need to control two things, or actually three things. So we have Schwarzschild written as the S squared, that um of S squared G star, where this M is now depending on epsilon or on K. If epsilon is the one parameter family parameter, or K is the sequence parameter. So we need to control, for one, the epsilons or the K's, and see that for different masses, these different Schwarzschild radii profiles behave nicely on compact sets, and this is where the work for the weighted spaces needs to be done still. That we need estimates on those. And then, on the other hand, we cut it off at a certain value, and this value is of the form Sm minus delta m, where delta m is something small. So we need to pick, this Sm is prescribed in the Mantel-Lewis chain construction, so we cannot pick it, but we have to pick this carefully, which is related to the cutoff, to get control on it as, so it depends on epsilon or k, to get control on it as epsilon goes to 0, k goes to infinity. It needs to be picked and controlled. And then the opening up, the bending in, happens between the Sm minus delta m to Sm. And so we also need control on this parameter Sm, where the bending inward starts. And this we cannot pick because it's prescribed with the procedure. Okay, so I repeat this in the Schwarzschild piece. First of all, we need to get control on the radial profiles in this S coordinate of the various Schwarzschilds of the different masses, where which one aspect of this is to see that the masses converge to this m infinity in the theorem. And also we need to get control on where we cut this off, which is something we need to pick, and previous papers only needed to show that we can pick it somehow, and we need to pick it somehow more uniformly, and then get enough control in it to get all the ingredients for the estimates we need later. And at the same time, we need to control the SM where the end bending in starts, which is prescribed by the procedure. And what we need to do is control it in terms of estimates. So that's the job we have to do on this orange-red part in the sequence. So what remains to be discussed, and what is actually the most subtle part of both the procedure and the estimates is the bridging part, so the part in the middle joining these two with positive scalar curvature that will also involve some modification. And there we need to do two things. So I said vaguely in the second part of the talk that we have this color and we have this bent-in Schwarzschild, and both have positive scalar curvature, and then we need to construct some bridge, and all of this is in the part where everything is spherically symmetric, so some spherically symmetric bridging manifold metric, which has positive scalar curvature and matches nicely enough when joined to either end. So to the blue bridging color part or to the orange Schwarzschild part. And so for that, we first need some idea how to bridge it per se. So say we get C11 regularity at both the ends of the bridging region. So this is called a bridging profile. This is a guess, so matches C11 and the boundaries. And then the Mantelidis chain paper and the other previous papers I mentioned, where this was used, it was enough to know that some bridging profile exists, which has the properties I mentioned. For us, we need some specific bridging profile depending on the parameter epsilon or k, whatever you want to call it, on which we can get quantitative control. So we need to tailor-make such a bridging profile. Tailor-made, doesn't involve any Taylor expansions, to be tailor-made for our purpose. So I indicated as some modification of this. And then integration. The details are of course in the paper, which will be on the archive soon. But we need some very specific bridging profile. And then in addition, once we have this bridging profile, which possibly has C11 regularity but not C2 regularity gluing across to the bridging region, color region, and also to the Schwarzschild region, then we need to modify, and also we need to control our modifications, because modifications have parameters, and these parameters need to be controlled in terms of the epsilon or k parameter in our sequence. So we have to have an explicit modification, which is quantitatively controlled in its scaling behavior. Okay, and this needs to be tailor-made. So these are the steps, the bridging profile and the explicit modification. That need to be resolved. And of course the picking of the A and then getting all these estimates that I'm just telling you to get also is some work. But then having made all these tailor-made profiles and all the estimates involved, we get a very nice control on all the parts, the color part, the bridge part, and the Schwarzschild part, including the bending in and the cutting off of the Schwarzschild. And of course, also of the Schwarzschild part, you get quite some understanding of on compact intervals, and not yet so well all the way down to infinity. In this coordinate, of course, in the usual coordinate, you know exactly what it behaves like. So all of this, then, hoping that the battery of my pen has recovered, allows us to get the metric of the form v at some parameter s and some point p on the sphere equals v of s and p squared ds squared plus some f epsilon of s squared g p of s, for s in 0 infinity and p in the sphere. And s now is the same parameter as the s used in the Schwarzschild radial profile and is a rescaled parameter of this parameter t on the color. And the VSP is a function that is different in different regions in the color, in the bridging, and in the Schwarzschild parts, and in the bend part. And the f epsilon is the radial profile, and the g of s is the one parameter family we've discovered before. We've used before that Matthieu Desentien wrote down using the uniformization theorem, which ended in a round sphere, and we just continue it by the same round sphere for larger s beyond this color region to write down this metric. And so we have this metric, and this metric is a special case of the construction of Matthieu Desentien for each epsilon. So in particular, it's geodesic complete up to the inner boundary. The inner boundary is minimal and strictly auto-minimizing. It's isometric to Schwarzschild outside some value, where Schwarzschild is also cut off at some value. It is positive scalar curvature, and I hope I didn't forget anything. Oh yeah, it induces the right metric, the correct metric on the boundary, namely G0. So all the things we wanted, but in addition, we have that we get none of the things that don't have an epsilon index, so none of the things except the radial profile little f epsilon depends on epsilon. So if we want to get estimates on uniform or C1 alpha convergence, we just need to estimate f epsilon. Uniformly in epsilon. And of course f epsilon prime. And our deal to get the C1 alpha convergence is to also estimate f epsilon double prime on, and now some integral 0 to some capital S is the place where we need to estimate this for any positive S. And we get uniform bounds. Let's have bounds in terms of the initial data. It's the metric on the inner boundary, and of course, depending on the choices we make, but not depending on anything else than our definite choices and the inner boundary metric. And then we can also show that f epsilon converges to a function f infinity, and f epsilon prime converges to the prime of that function infinity pointwise on the interval 0 infinity. And by standard arguments, including Arzela-Ascoli, we get the C1 alpha on compact subsets convergence. This is Arzela-Ascoli. Yeah. Okay, so that's the analysis that enters at the end. And the limit f epsilon is what constitutes, via the same formula here for gamma. If you put f infinity instead of f epsilon, constitute the gamma, the metric gamma infinity, and I should put an epsilon here. So if epsilon is 0, then this will be gamma 0, or if k goes to infinity, this will be gamma infinity. So the only thing we needed to control is this radial profile, everything else didn't become an epsilon. epsilon. And this is how, so the limit metric has the same almost warped product shape with the same function v and the same the metric g of s on S2 for fixed s. And the limit function f infinity is constant 1 for while, corresponding to this constant area cross-section cylinder, and will then grow to the radial profile of Schwarzschild eventually for the right mass m, with some bridging in between for the f epsilon, and no bridging in between for the limit, where it just attaches in C11, not C2 fashion. So we have f epsilon, f infinity explicitly just as f epsilon, and can see the properties there. And before I end, I wanted to make one comment on why we use this eigenvalue to be positive for the initial metric that we prescribed, and the simple answer is, of course, because Mantel-Levy-Simshane do this and because this works. But the more interesting answer for the experts is that this is some kind of possibility to ensure that if this surface, which is S2 with this metric, if this metric has this property, then the surface sits inside a Riemannian manifold as a minimal boundary, then it will be strictly stable. Yeah, so that's some kind of a priori ensuring that it will be strictly stable. So somehow, when we construct strictly outward minimizing boundaries, we already put in some version of being strictly stable. And then, of course, this goes back to Mantel-Levy-Simshane. It isn't my idea. And with this, I would like to thank you for your attention, bearing with me through probably all 3 videos, and I'm curious to hear your questions. Thank you.